I'm going to talk about embedded software. Specifically, I'm going to talk about the issues around power consumption of devices and the fact that this is now a software issue. I find it very interesting. Embedded software, of course, is right at the interface between software and hardware. So I'm not a hardware engineer, I'm a software engineer, but I find it very interesting looking at the connection between the two. And the recent change, which has been, or recent trend, should I say, towards power being a very important issue, has actually had some interesting impacts on software. And that's what I'm going to talk about this morning. Now, this session does have some technical content, although I will not go into too much detail. But I wanted to give you a flavor for the kinds of things that are of concern to embedded software engineers. So, here is my agenda. It looks quite long. It's not really. There's a number of areas to cover. So first of all, some introductory remarks, and I want to make you think a little about power, about electronic devices and the power they consume. I rather imagine that everybody, well, maybe almost everybody, has something like this with them at this moment, a high functionality cell phone of some kind. And you have this in your pocket or in your bag, and you use it, and you probably find you charge the battery a little more often than you would like, but it works okay, doesn't it? It does the job for you, but there's room for improvement. Before I explain some of the problems that we are addressing and how we are addressing them, I want to give credit to the guys who make these things. Because if these guys were not experts in optimizing power, your phone would look a little more like this. In other words, it will be bigger, it will be heavier, it may have the same battery lifetime, but as you see, it would probably make you walk like this. Another feature of this mythical phone would be, it would probably have a fan. Imagine everybody in the audience with their phone going whir in their pocket. That would make an interesting background to a presentation, which I would rather not have. So these guys have already done a good job, but there's still room for improvement. There's still room for improvement in many other kinds of embedded device. The importance of power is growing quite steadily, mainly for complex battery-powered devices, although for environmental reasons, we obviously want to reduce power consumption of everything. So the issues apply all over the place. If I was talking to you 5 years ago, I would have said that around 50% of embedded systems are connected in some way, networked in some way. Now I would say it's more like 75–80% of embedded systems, and connectivity is expensive on power. As soon as you have Wi-Fi or cellular connectivity, you're consuming considerably more power. The problem to date has been power optimization has been done late. It's been done at the end of the development cycle, and software engineers have barely been involved. That is a problem. What you need to do is consider power from day one. The kinds of things we need to do, we need to choose the right hardware, kind of obvious. We need to allow the software to manage power. That may be obvious, but maybe not. This means you need to be able to choose the right operating system and drivers to go with that, and I'll talk a little about that. We need to define power usage profiles. We need to consider how power will be used by our device in order to optimize it. To do that, we need to actually set some goals. And those goals must be power-related goals which are measurable, and we must review those throughout the development cycle. They're not something which we can set on day one and check on release date. We need to consider them all the way through the cycle. This is an illustration which I think is quite helpful. We call this the power pyramid. And this really shows the relative importance of different aspects of a system to its power behavior. The most important thing is choosing the right hardware. Even though I'm a software engineer, I have to admit hardware has an important place to place in the design, and ultimately the hardware will define the power. However, it is also important to look at a number of other factors. Use cases, how you use the device, is the next most important thing. So looking at what the device's behavior is like. The next thing is the operating system you choose, if indeed you have one, of course. And then the next layer, and the layer within that operating system that's important is the drivers and BSP. And on top of that, the application software has the least impact in terms of improving the power consumption behavior of a device. It can actually have the most impact in damaging the power behavior of a device, but it can have the least benefits of improving it. So applications is least important. So hardware choice, first of all. As I said, it has the biggest influence on power consumption overall. That's kind of obvious. The features we need to look for in the CPU. We want to be able to turn off blocks of hardware. This is beyond the CPU, really. In an SoC, we need the ability to be able to turn off any parts of this system which are not in use at the current time. So peripheral devices, essentially. We need to be able to perform dynamic voltage and frequency scaling. In other words, change the frequency and the voltage of the CPU in order to adjust its performance and hence its power consumption. And we also want a CPU which has low power modes, so means of putting it to sleep in various ways so that we can optimize the power further in that way. We also must look at the system as a whole. The overall design must be compatible with these requirements. So the first thing to do is look at use cases. The use cases are the functions, the identifiable functions that a device performs, which may or may not have user interaction involved. And to illustrate this, I'm going to talk about a hypothetical medical device. It's a battery-powered device. It has an LCD display. And what it does is the patient carries this around, and it will display their vital signs. You know, their heartbeat, blood pressure, that kind of stuff. And it will upload that data via Wi-Fi so that the doctors, the hospital, can keep track of the patient without having to visit them and see them all the time. So a device might look like one of these things. These are just illustrations. What are the use cases for such a device? Well, there were 4 that we have identified. The first one is the device simply takes a measurement, so it measures all the vital signs. That's one use case situation. Another one is the device uploads that measured data via Wi-Fi. The third one is the user presses a button on the device and takes a look at their own vital signs. Patients tend to be quite interested in whether they're still alive or not. And the fourth use case is the device is idly waiting for the next measurement or something to happen. That's a realistic situation, of course. So what we need to look at is how much functionality each use case needs. Which hardware blocks need to be activated, therefore which drivers will be in use from the software perspective. We need to estimate the energy for each use case. The energy is a function of the power consumption versus the amount of time that that use case is occupying. We can also then take the frequency with which that use case is applied, so how often is the data uploaded, for example, and we use that as a scaling factor to work out the overall energy consumption in a day, for example, and we can figure out what the battery lifetime is likely to be as a result of that. So for this example, we have the 4 use cases down the left-hand side there, and what we do is we look at the average current, which is shown on the left-hand most column of numbers, how long that thing goes on. So the vitals measurement only takes a second. It consumes 158 milliamps. We do it 288 times a day, so that gives us a resulting 13 milliamp hours per day. And if we then perform the same procedure for each of the use cases, we arrive at the number on the bottom right-hand corner. And this enables us to decide whether the battery life is achievable or not. And we'll look at this kind of thing a bit more in due course. Having looked at the chart, we learn that the data upload is using most energy. It doesn't use the highest current. Actually, I'll go back just for a second. You see it uses only 158 milliamps, but sorry, I've got the wrong one there. The data upload uses 250 milliamps, but because of its frequency, on the right-hand side, we see the amount of energy it uses is 60 milliamp hours per day. So even though it's not the highest current, because we do it so often, it uses the most energy. So maybe uploading every 5 minutes is too often. Because realistically, are you going to change over a 5-minute period? Well, you might. Something drastic might happen. But maybe a better system would be to upload every 30 minutes anyway, but upload again on a special occasion if something changes. If your heart rate suddenly goes up or down or your blood pressure changes, maybe that's a good reason to upload it. So that could improve the energy of this particular use case drastically. The second largest check was the use case was vitals check. Now, this assumes that the display will remain illuminated for 30 seconds. That's where most of the power goes, is into the display. Nothing else is really working at that particular time. So a very simplistic way of reducing the energy here is cut down that timeout. Do you really need 30 seconds to absorb what your blood pressure and heart rate are? Probably not. And if you really can't quite take it in, you press the button again. But 30 seconds is probably far too long. 15 or 20 is probably quite enough. And that would make a substantial difference to the energy of that particular use case. So that's what the idea of use cases is all about. So analyze the functionality of a device. So the next thing on that power pyramid was the operating system. Now, most embedded systems are built on some kind of operating system, either a real-time operating system or Linux or something like that, depending what's required. And this can have a significant impact on power saving because the operating system is to some extent the interface between the application code and the hardware. And for this to be very useful, the operating system must support some of the power features, like dynamic voltage and frequency scaling and the different sleep modes of the CPU. The most efficient way that an operating system can do this is to have a native power management framework. So in other words, have power management built into the operating system, not an add-on application, if you like. So BSPs, the board support package, must be written to support the power issues, to address the power issues, because that's the bit which is close to the hardware. Every single driver must have well-defined power states, because we know what different hardware can do. Maybe, for example, a given piece of hardware may be quite stable to be turned on or off, but it may only work at a particular frequency. On the other hand, a piece of hardware may be very relaxed about what frequency the CPU is running at in terms of its stable functionality. So we need to know how a given piece of hardware will respond, and that in turn, from the software perspective, gives us an idea of what each driver can do. So from a conceptual level, the power framework looks like this. So we have on the center of this diagram the application software. Around that is the real-time operating system and its power management framework. And around that is the actual hardware that's doing everything. So the application is completely insulated from the hardware issues by the operating system with its power management framework. So the BSP and the drivers is the important part of the operating system, the bit which is close to the hardware, and therefore the bit which will have the most influence. So what we need to do is to look at each driver and to look at its power management requirements. First of all, we need to look at what power states it supports. So possibilities here are on, that's kind of obvious, and off is another obvious one. But there may be power, low power states the CPU can be in, like standby and sleep, and we'll talk a little more about those in due course. But are these supported by a particular device, and hence does the driver need to be informed accordingly? The more important one is what operating points can the driver be used at? Now, an operating point is a combination of voltage and frequency, which defines an overall power consumption of a CPU. And as I mentioned, a driver may or may not be functional at all frequencies. So the kind of thing we might have is we might have a device which, whilst it's on, it can work quite happily at 200 megahertz and 100 megahertz. That sounds perfectly reasonable, I suppose. And in sleep mode, it may need just a 1 megahertz clock, which is a drastic reduction in power consumption. We need to know whether a driver can participate in DVFS. In other words, It may have an influence on DVFS, or it may simply need to be informed that the frequency has been changed. The last one's more subtle, and that is direct memory access. Sometimes a device will transfer memory to or from memory, sorry, a device will transfer data to or from memory without the CPU being directly involved during the transfer. So the CPU will typically initiate the transfer, and the device will carry on doing it, and the CPU will get on with doing something else. Well, what if the CPU does that, starts the data transfer going, and then says, oh, phew, I can have a bit of a rest now. Let's turn the frequency down, lower the voltage, and have a nice little siesta. Actually, that would be a good name for a low power mode, the siesta mode. That would be quite good, wouldn't it? Well, that would be okay, but the DMA transfer is still carrying on. And if you reduce the frequency of the CPU, that's going to affect the frequency of the bus and hence the transfer, and that could, well, potentially, it could mess things up comprehensively. Broadly speaking, though, the driver needs to be able to indicate to the CPU that it does DMA transfers, and therefore, please don't pull the plug on me while I'm transferring data, is the gist of it. I quite like siesta mode. I must write about that. I talked about low power modes. Different CPU manufacturers have come up with different ideas. Interestingly, there is a general trend with embedded software that a lot of the technology that we use was first encountered on the desktop. This has been the case ever since I can remember. In the earliest days of embedded software, we started using high-level languages, but by the time we did that, it was long after the desktop guys had completely standardized on high-level languages. And the reason why embedded software appears to be a little behind is twofold. Partly, it's the nature of embedded software engineers who are very conservative. They don't use something unless they're really confident about it because they need highly reliable systems typically. But also, we're always very concerned about resource usage and so forth, and therefore getting it exactly right matters. If you're programming a PC, for example, as you're aware, PCs have infinite amounts of memory, they have infinite amounts of CPU power, and they cost nothing. So given that programming environment, if that's what you're used to programming in, when somebody says, okay, this CPU has fairly limited power, just enough to do the job, and it has only a limited amount of memory, plenty, but still limited, and we don't want to spend more than a few cents extra on additional hardware, it's a very different programming environment. That's why embedded software and desktop software are so different. Something we have acquired recently from the embedded software world is low power modes. You're probably very familiar with your laptop. Typically, you shut the lid, and it will go into standby mode. You open the lid again, and it wakes up. If you leave the lid closed for too long, it goes into hibernate mode, and when you open it, it takes a little longer to start up. From the user's point of view, that's all that really happens. The embedded software engineer would need to know exactly what happens, why it happens, when it happens, and what are the implications of that. That's why we've taken a while to get there. So typically, there are two low power modes which correspond to suspend and hibernate on a PC. In fact, we tend to use the same names so that we know what we're talking about. In suspend mode, all the hardware is switched off except for the memory, and that is retained at the lowest possible power level on self-refresh mode so that the data in there is protected. Hibernate mode, absolutely everything is switched off, but only once the content of data has been written to some non-volatile memory. Now, on your PC, that's written out to disk, but obviously on an embedded system, you're unlikely to have a disk available. It's more liable to be written to flash memory or something of that ilk. So those are the two possible modes we have available, and these are very attractive in reducing power consumption because obviously suspend is going to reduce power quite a lot because you are only keeping memory running. Hibernate is going to reduce power to almost zero. Not quite zero, but almost zero. So they have some very interesting attractions. However, there's usually a however, the cost of entering and exiting these modes needs to be considered. There is a power cost. The power cost is you've got to execute code in order to get yourself into a good state to recover from suspend and hibernate. And in the case of hibernate, you've got to write the data out as well. So that's all power-consuming activity. There is also time. if you make the device respond too slowly as a result of it having to come out of suspend or hibernate, the user will probably leave it switched on more and will end up consuming more power. So you need to make sure these things are not going to get in the way of the use cases that we talked about before. The amount of power it consumes getting into one of these states and getting out of it depends how much of the system was on when it went into the low power mode. If very little of the system was switched on, there's very little data to save, so the cost of going in and out of suspend or hibernate is quite small. As I say, the cost of storing the RAM into flash in hibernate mode is probably the biggest one here. That can be minimized by making your application as small as possible, so there's as little data to be saved as possible. You can even do clever things like, well, you only store the RAM data, not the RAM code, because obviously the code is not changed from last time. The code's fixed, but it may be loaded into RAM for execution purposes. So you only save the data, but when you restore the RAM, you have to restore the code and the data. So there is room for optimization there. A little bit of a worry is system lifetime. Flash memory withstands a certain number of cycles of use. Now, you can do wear leveling and all kinds of clever things to maximize that, but there are limitations. Modern flash has much better lifetime than it used to have, and I was only reading this week about some technology for revitalizing flash chips and giving them even more life. I think you just heat them up to 150 degrees for half an hour or something like that, and they come back to life again, or something silly like that. Not very convenient in an embedded system, but it does show that maybe long-term this is not a worry. But for the moment, we better keep this in mind. This last factor means maybe we want to limit how often we use hibernate mode, because too often will be a problem. So overall, we need to look at whether the power benefit offsets these costs. So for our example device, the measurement interval would imply various things. How often would wake up be required? If the measurement interval is made much longer, we need to wake up the device less often. Having said that, though, being a medical device, I would rather it didn't wake up every half an hour, because a lot could happen to me in half an hour, and I would want this device to keep an eye on it. So we need to bear that in mind. So the measurement interval is a good example here, where I would come out in favor of a frequent measurement interval and not using suspend in that context. But this needs to be considered very carefully. We come on to the application layer of the software, the one that has least impact on power. Now, this is the last layer of software we're going to consider. And actually, badly written code can have a very negative effect on software, on the power consumption of the software. And the benefit of using an operating system with a native power management framework is the application engineer can actually proceed without really having a lot of knowledge about the underlying technology. He simply uses devices as he needs to. The devices themselves keep the operating system informed about their power requirements. So the operating system does all the heavy lifting. So the application code writer can, to some extent, be abstracted from it, in the same way that most modern embedded software developers are application specialists rather than embedded software specialists. It's another challenge, because they still think they have infinite memory and infinite resources and all that. Typically, an application is written as a number of tasks. These are quasi-independent threads of execution. And in a very simplistic way, this isn't the detailed way that power management works, but broadly speaking, if you imagine each task or each group of tasks has a set of power needs because it corresponds to use cases, it will define which peripherals it needs and hence which ones need to be switched on by the drivers and what the minimum operating point is into the frequency and voltage. And the OS will take care of actually making those things happen. So the application code doesn't really need to do very much at all. I mentioned at the beginning that you need to think about power all the way through the cycle. And to do that, you need to make measurements. So power should be measured and be considered an issue from day one, not something you come back to later. It's possible by planning you plan this by setting the power requirements for drivers. You define those use cases I talked about, and you map the use cases to your application. You do it that way round. You don't come back to it later. All software engineers should be equipped to measure power. Now, that may sound a rather perverse thing to do, because at present, a given software engineer will have instrumentation available. Now, instrumentation may be electronic devices, it may be software tools they use, but those tools will let them execute their software, trace what it's been doing, control its execution, measure its performance, look at the hotspots in the performance. So we do performance measurement regularly to find out when the CPU is working hard, for example, and maybe when we're not meeting deadlines and things like that. Those are the things that software engineers do. What I'm suggesting is that in addition to that, wherever possible, the software engineer should have the means of seeing what the power consumption is of their target system. Now, you might say they don't have a target until the end, because the hardware and the software tend to come together quite late in the development cycle. That's true, but there are plenty of simulation environments around nowadays that will give you at least a pretty good idea of what the power will be as well. The trick is simply to, firstly, present that information to the software engineer in a way that they can see power against software execution. And the really, really hard thing is to get the guys to care, because software engineers just haven't had this in their minds up till now. Biggest challenge is social, not technical. We need to achieve that by having a philosophy that meeting power consumption goals is part of the spec. So to date, a specification might say the software has to be within this memory size, it has to perform this functionality at this speed, and respond in this particular time, that kind of stuff. We now need to say, perhaps, and consume this amount of power. So, for example, if you have a Wi-Fi driver, it needs to work well with every possible wireless network. That wasn't always the case, but it tends to be the case nowadays. But we could add to that, it must be able to be turned off and have its power consumption reduced to 0. And when you turn it back on again, it must be fully functional. Now, an obvious thing to ask for, have you seen that in a software spec? Probably not, but you probably should. And by the way, that functionality needs to be repeatable, so we need to test it. Say 100,000 times will do, just to make sure that it is totally repeatable. Drivers need to have their power functionality completely tested, because it's all well and good saying a driver is power aware. We need to make sure that it's properly enabling and disabling hardware. That requires a lot of interaction between the software and the hardware engineers to make sure that everything's happening like it should. The participation in DVFS must be verified, and we must make sure that DMA problem is addressed properly, because that could generate very, very subtle bugs. If a data transfer has occurred sometime in the past and had an error, the bug will pop up much later. So actually finding that's very hard. So making sure DMA transfers are occurring is vital. To give some example sort of numbers, just to give you a feel, here is a profile for a device. We have 4 operating points, 4 different frequencies, together with Hibernate and standby. And this gives the current consumption for each of these. This is on an IMX28 board. And you can see what the various current consumptions are there. Now, if we then take those operating points and consider what percentage of the time they were used for, this gives us a milliamp hour energy consumption in the third column there, and gives us a total of 126 milliamp hours, which for this particular device, using the Nucleus real-time operating system with power management, yielded a 19-hour battery life. Is that good enough? But depends what the device is, doesn't it? That medical device, that probably would be good enough. That means that for the whole waking day of the patient, they can have the device on battery power. They can charge it while they're asleep. That sounds good enough to me. This assumes those estimates are good. And things like Hibernate going down to 0 is quite interesting, and this has a 40% hibernation time. That's quite a lot. But it's a reasonable profile. What if we didn't have power management? What if there was no power management at all? Well, actually, we would do everything at operating point 3, because we have no other option, because we can never If you had no power management, you can never afford to lower the frequency, because what would happen? You don't know. And therefore, we will consume 470 milliamps all the time, and that will give a 5-hour battery life. And in broad terms, that ain't good enough. So for this particular design, power management is totally non-optional. At the end of the cycle, you should end up with a design which has got good power performance as you specified. However, there may be room for more optimization. Don't shut your eyes to that possibility. Do a final review and look for other possibilities. There may be different operating parameters you could apply. There may be new use cases you can define. I'm not going to invent any just to illustrate that. But it's always worth being open-minded. Even if your design is set in stone, think about it at the end of the cycle, there may still be opportunities. A few conclusions and a short story. A few conclusions. The key thing is embedded software developers need to think about power from now onwards. It's not optional. It's no longer something they can say, oh, that's a hardware issue. Support for low power hardware features is essential. That's kind of obvious, but needs to be reiterated. And for a complex software application, it's just not possible to put off power until the end. You need to do power optimization all the way through the cycle. I'm going to wrap up with a short story. This is a true story about a friend of mine. He's not a mental graphics guy. That may become obvious. But he had a recent experience which it made me smile, and I hope it will make you smile as well. But I just emphasize this is a true story. This guy purchased a new cell phone. This isn't an actual picture, but it gives you an idea what a cell phone looks like in case you haven't seen one before. So here's the conversation. He comes into the office. Hey guys, I got a new phone. Yeah, what's it like? Well, it's just like an iPhone, only much cheaper and even better. This had our attention. Better? Yep, it can take 2 SIM cards. So I can use the phone for both business and personal calls. No more carrying 2 phones. Sounds useful. Apple, are you listening? Cool. Where did you get it? Oh, on eBay. It came from China. Okay. Sounds good. Any downsides? Well, it is a bit power hungry. How bad? What's the battery life? About 3 hours. Unfortunately, I thought the response to that was inappropriate for an international audience. But you can probably translate that into your own language. You can imagine what reaction 3 hours would have. But it's okay. They do supply 2 additional batteries, and it's really great. So that's a true story. This guy was very excited about it. So what this shows is you can ignore power management entirely and produce a device which is almost totally unusable, and somebody somewhere will still buy it. But this is not an Apple product, so and I don't think Apple are worried about this particular competitor. So thank you for your time this morning. If you wish to contact me after today, there is my email address. And I do write a regular blog on embedded software and whatever happens to be on my mind. And there is the address, and I think you have a copy of this information in your handouts and so forth.